Every year, over 20 million metric tons of copper are mined worldwide. But only 1% of that massive amount makes it into the shape we see every day, as thin pipes that cool our homes, offices, and skyscrapers. This story begins in the giant mines of Chile, where excavators as tall as 5-story buildings dig up the ore from which a gleaming pipe is eventually born. From explosions in quarries to magma in furnaces. From thousands of degrees to surgical precision. How does a piece of mountain rock turn into an air conditioner? We're about to show you the whole journey, step by step. Deep underground, in the deserts of Chile, the steppes of Kazakhstan, and the mountainous regions of Australia, work is buzzing, slow, monotonous, but extremely important. Here, copper ore is extracted, the raw material from which thin, shiny pipes for air conditioners are later born. This process begins far from factory workshops, in giant quarries, where every explosion, every excavator bucket, is a step towards the metal that will cool rooms in skyscrapers and apartments. In Chile, which produces nearly a third of all the world's copper, there are giant open pit mines. For example, the famous Escondida. Here, mining machines as tall as a 5-story building slowly move down the terraces, scooping up rock from which only 1% of copper is extracted. Imagine, to get 1 ton of metal, you need to crush over 100 tons of rock. After extraction, the ore goes to crushers, huge machines that turn rock into pieces the size of a walnut. Then, even smaller, down to sand. This sand goes to flotation plants. There, using water, air, and chemical reagents, copper floats to the surface as foam, which is skimmed off, dried, and sent for smelting. All of this is heavy, energy-intensive work, but without it, there would be no pipes, no air conditioners. From the first blast in the quarry to the thin pipe in an office, the journey takes months, covering thousands of miles. And each stage is a story of its own. Raw ore isn't transported to the factory where copper pipes for air conditioners are made. That would be too bulky and inefficient. Instead, after concentration and primary processing, it's turned into a more concentrated, transportable product. Depending on the supply chain, the factory might smelt the concentrate or mat themselves, producing pure copper if they have melting facilities. Or they might purchase cathode copper in the form of plates and then form blanks for pipes from it. Shiny rectangular plates. These are copper cathodes, weighing up to 200 pounds each. They are stacked on pallets and brought to the factory in incredibly long trucks. This is almost pure copper, over 99.9%, and it will become the heart of future pipes. But first, it will turn into red-hot ingots. Cathodes are removed from pallets and inspected, checking for cracks, oxidation, or dirt. Next, they need to be cut for remelting, as they are incredibly large. The cathodes are placed one after another on a hydraulic table, and a heavy-bladed press descends from above, literally chopping the copper in half. The sound is a dull metallic thud, almost like a gunshot, quick and precise. When more complex shapes or smaller volume are needed, a bandsaw with carbide teeth is used. It slowly but steadily cuts the copper, like wood, only with water cooling, because the metal heats up. If the copper needs to be cut at the melting location, a plasma cutter or an acetylene torch is sometimes used, a stream of burning gas that melts the metal along the cut line. But for cathodes, this is less common. It's too expensive a technology. All operations are usually automated. Cathodes are brought by a crane or forklift, loaded onto a conveyor belt, and everything moves down the line. The cut pieces are immediately fed into the furnace. The operator only ensures that everything moves smoothly and without jams. The cut pieces fall onto a metal roller or chain conveyor. There they lie flat, often in a single layer. If needed, they are separated by special pushers to prevent them from sticking together or getting stuck. This conveyor works slowly but powerfully. The task is to continuously feed copper into the furnace without creating bottlenecks or downtime. After melting, fluxes are added to the molten metal, substances that collect impurities and scale, help keep the copper clean and shiny, and reduce slag formation. The fluxes float to the surface as a dark film, which is scooped up with a mechanical skimmer and discarded. As soon as all the copper has melted and become a uniform, shiny mass, the temperature is equalized and the furnace opens from the bottom or tilts, pouring the metal into casting molds. The molds resemble long, rectangular boxes with thick walls, made of strong steel capable of withstanding intense heat. The furnace is tilted, or a valve is opened, and the hot molten copper begins to flow along a special channel, like a bright orange river of magma. This channel leads to the mold, which stands ready to receive the metal. The mold is cooled by water or air, so the copper entering inside begins to solidify quickly. Immediately after pouring, the mold is often lightly tapped or vibrated a bit. This helps air bubbles and voids escape from the molten metal, ensuring the ingot is strong and without defects. The mold stands on a special platform that sometimes moves or tilts slightly, helping the metal distribute evenly. The hot steam rising above the mold resembles volcanic smoke. Workers in special protective clothing observe the process, ready to intervene if something goes wrong. As soon as the copper in the mold cools and solidifies, the mold is opened and a long, shiny ingot comes out, a large piece of copper, ready for further processing. These ingots can weigh hundreds of pounds and look like metal bars with a smooth, shiny surface. The ingot that came out of the mold first undergoes quality control, checking its weight, shape, and absence of cracks or defects. Then it is heated to a certain temperature to make the copper softer and more pliable for further processing. Next, the ingot enters a large rolling mill, where it is gradually rolled between rollers, stretching and making it thinner. Rolling happens several times to make the ingot longer, thinner, and more uniform in thickness. After rolling, the metal undergoes special forming. It is turned from a flat strip into a cylinder, which is then welded along the seam or blown into a pipe shape. This process is very precise. The diameter and wall thickness are regulated with great accuracy so that the tubes can withstand pressure and don't burst. After forming, the copper tubes are still hot, almost like a freshly baked bun. To prevent them from deforming and to keep their perfect shape, they are cooled quickly. For this, the tubes are passed through long pools of cold water or special cooling baths. Water sprays from different sides, flowing around the metal, and it cools down instantly. Then, the most interesting part begins, checking the dimensions. The tubes pass through special calibrating devices. This can be a set of rings or sensors that measure the pipe. Each ring corresponds to the exact inner or outer diameter. If the tube passes through the ring without problems, the size is normal. If not, an automatic sensor signals, and the operator stops the process. If the pipe meets the standards, it is sent further, for cutting or packaging. If not, it is returned for rework or recycled to prevent defective products from reaching the customer. After the copper tubes have undergone forming, cooling, and calibration, they proceed to the next important stage, cutting into standard or ordered lengths. This process is very important, as the quality and ease of installing the pipes in air conditioners depend on the accuracy of cutting. The tubes are usually supplied in the form of long straight sections or coiled into bundles. First, they are uncoiled or fed along a conveyor to a special automatic cutting machine. This machine is equipped with a powerful cutting disc or saw that rotates at high speed. The operator sets the precise parameters for the cutting length, for example, 10 feet. The tube is fed forward, and the machine precisely cuts off a piece of the required length. The moment the cutting disc touches the copper, sparks fly, and the metal almost hisses and smoothly separates into two parts. The movement of the disc is very fast and smooth, so the cut is even and clean, without burrs or cracks. The finished tube sections are packaged into bundles or boxes, often wrapped with tape for easy transport. Each package is marked, indicating the tube dimensions, wall thickness, and production date. Every second globally, over 3 billion gigabytes of data are transmitted. But did you know that all this happens thanks to a thread thinner than a human hair? and that this thread starts with ordinary sand. Not beach sand, but perfectly pure quartz, where there's only one impurity per million parts. To create fiber optic cable that transmits light at a speed exceeding 300,000 kilometers per second, you have to go through a journey involving chemical vapors, sterile laboratories, a 2,500-degree furnace, and lasers that monitor every microcrack. This process looks more like manufacturing a spaceship than a cable, but it is the foundation of the internet you are using right now. To create a thread capable of transmitting light at a speed exceeding 186,000 miles per second, you have to start with sand. But not just any sand, only special, extremely pure quartz sand, where the main substance is silicon dioxide. For fiber optic production, sand with a silica content of over 99.9% is used, meaning in 1 million parts, there's only 1 part of impurities. Imagine this. In every pound of raw material, no more than a few millionths of an ounce of impurities. And this is critical, because even 1 billionth of an inch of foreign metal or organic matter can cause light scattering or absorption in the fiber optic cable. And then the signal, which was supposed to travel 60 miles without amplification, simply disappears. Raw material for fiber optic cable isn't just washed or filtered, it's purified at the molecular level. Manufacturers often use vapor phase chemistry. Quartz sand is converted into gaseous silicon tetrachloride, which is then distilled, filtered, and deposited as pure vapor. And only then is it converted back into glass. Add to this strict control of temperature, humidity, air currents in clean rooms, and you'll get an idea of how far this is from an ordinary sandy beach. Production laboratories look more like National Aeronautics and Space Administration sterile zones than a glass workshop. And all for the sake of ensuring there's not a single defect in every yard of the future fiber. Because when you're transmitting light over thousands of miles, even one microscratch can cost you signal quality. A large transparent glass cylinder that will later be melted and drawn into a very thin thread. This is the fiber optic preform. This huge glass rod is made using a method called vapor deposition. In a large furnace, air is mixed with very pure gases. These are different substances that turn into vapor when heated. These vapors hit the inner surface of a transparent tube, which is heated very intensely. When the vapors touch the hot wall of the tube, they deposit and turn into tiny droplets of glass, like dew collecting on leaves in the morning. Gradually, these droplets collect, layer by layer, until a thick layer of glass forms inside the tube. Then this tube is heated even more intensely, and it collapses into a dense, solid rod. And this is our preform. The preform is placed in a special furnace that heats up very intensely. The temperature inside it reaches approximately 4,700 degrees Fahrenheit. This temperature is so high that the glass becomes soft and starts to melt, like caramel on a stove. When the end of the preform melts, a drop of molten glass begins to drip from it. This drop is very carefully drawn downwards, and a thin thread is formed from it. This thread, the optical fiber, is drawn at a speed of approximately 1,000 feet per minute. Imagine that. It's faster than a cyclist moving through the city. It's important for the thread to be of uniform thickness throughout its length. The thickness of an optical fiber is usually around 125 microns, or approximately 0.005 inches. That's very, very thin. For comparison, the average human hair is about 100 microns thick or less. To keep this diameter under control, special instruments are used during the process. They look at the thread in real time and measure its thickness. If the thread starts to become thicker or thinner, the system automatically changes the drawing speed or the furnace temperature to correct it. After the optical fiber has been drawn from the preform and has become a thin, transparent thread, it needs to be protected. The fiber is very thin and fragile. If left unprotected, it can easily break, cracks will appear, or dirt will get on it. Therefore, immediately after drawing, the fiber is coated with a special protective layer. A thin thread is pulled from the furnace. After the furnace, the thread immediately goes into a coating machine. This is a special device that clothes the thread in a plastic sheath. The optical fiber enters a special part of the machine called the coating head. It's like a small tube or nozzle, inside which there's molten protective material. As the fiber passes through this tube, a layer of liquid polymer is evenly applied to it. The polymer has very low viscosity, so that the coating is thin and even, but dense enough to protect the fiber. This coating layer usually consists of two parts. The primary coating is a very soft, elastic layer that dampens mechanical shocks and allows the fiber to bend. The secondary coating is harder and more rigid, protecting against external influences, dust, and scratches. These two layers are applied sequentially, one after the other, to provide reliable protection. After applying the liquid coating, the coated fiber passes through special forming rollers. They regulate the thickness and evenness of the layer, pressing the coating uniformly along the entire length of the fiber. These rollers are very precisely calibrated so that the layer is not too thick or thin. After the polymer has been applied and shaped, the fiber passes through a zone of ultraviolet light. Here, the polymer instantly hardens under the influence of ultraviolet lamps. This is a process called polymerization. Anyone who gets their nails done knows how this happens. Ultraviolet lamps emit light of a specific wavelength that activates chemical reactions in the polymer. Thanks to this, the coating quickly becomes solid, while retaining its elasticity and ability to protect the fiber. This is a very fast process. The coating solidifies in fractions of a second, literally. This method does not heat the fiber, so it doesn't damage it. This provides very strong and durable protection. The entire machine is equipped with sensors and control systems. They constantly measure the coating thickness, fiber feed speed, and uniformity of application. If the coating layer is too thin or there are defects, the system either stops the process or adjusts the parameters to avoid defects. At the end of all this technological magic, a spooling module, rotating with a hum resembling the sound of a jet engine, only in miniature. The fiber, like transparent silk, lies down smoothly and precisely, coil after coil. It shimmers in the light of the lamps, reflecting cold blue and white hues. The spool moves smoothly, to the left, then to the right, with millimeter precision, as if an artist is painting pictures with movement. One wrong angle, and everything will go haywire. So the system automatically adjusts the rotation speed and fiber tension with surgical precision. Around are sensors, lasers, cameras. They carefully ensure that the fiber lies flat, doesn't twist, and doesn't create tension. With every minute, more and more layers appear on the spool. Imagine, in a few hours, there are already several feet of thin, almost invisible fiber there. And all this, without a single break, without a single scratch. Because even a micro crack, and the light signal will get messed up, like a radio wave in a storm. Before cable assembly begins, the fiber from the spool is carefully wound onto a production line. Since one cable usually contains several fibers, individual threads are combined into ribbons or modules. For ribbons, the fibers are arranged parallel in a single plane, for example, 12 pieces, and glued together with a special resin. This makes them easier to work with during connection. For bundles, the fibers are twisted into a spiral strand and placed in a plastic tube. These ribbons or bundles are then placed into buffer tubes, thin, flexible plastic channels that provide space for the fiber's slight movements. This is important because when the cable's temperature changes or it's bent, the fiber slightly expands or contracts, and the buffer tube helps prevent it from being damaged. A gel that repels water and absorbs vibrations can also be added inside these tubes. Around the buffer tubes, strengthening elements are added. Fiberglass or Kevlar, very strong threads that protect the cable from stretching. Metal wire, for additional mechanical strength or grounding. A central strength member, a rigid element in the center that maintains the cable's shape. These reinforcements are needed so the cable can withstand tension, impacts, bending, and remain intact for decades. All of this is wrapped in an outer jacket. This is a dense plastic or polyethylene pipe resistant to ultraviolet light, moisture, rodents, temperature fluctuations. The cable is tested. The bandwidth of each fiber is checked, as is its bending strength and resistance to moisture. Then it's wound onto large drums, marked, and technical documents are added, and it's ready for transportation and installation. 850 horsepower. That is the power output of the hybrid Lamborghini Revuelto. This is almost like having the force of 2 average tanks. Whenever you see a Lamborghini on the road, it is impossible not to turn your head. This is a car that shouts success and style, and it does so very loudly thanks to its V12 engine. A Lamborghini is not merely an automobile. It is a symbol of status, luxury, and wildly high speed. However, this car is not just beautiful. Its heart is a genuine masterpiece of engineering. Shall I tell you about the engine? Lamborghini is renowned for its naturally aspirated engines that roar like a wild beast. The brand's most famous motors are the legendary V10 and V12, which provide not only insane power, but also an incredible sound that sends chills down your spine. The V12 engine was already present in the first Lamborghini 350 GT from the year 1963, and it remains the company's signature to this day. The establishment of Lamborghini was not merely a business project, it was an act of revenge. In the small town of Sant'Agata Bolognese, under the blazing sun of Emilia-Romagna, a company was born that challenged none other than Ferrari. Ferruccio Lamborghini was a successful businessman who became wealthy through the production of tractors. He owned an entire collection of sports cars, but he had problems with the Ferrari 250 GT because its clutch often broke down. One day, Lamborghini decided to express his dissatisfaction directly to Enzo Ferrari. He proposed improving the cars, but he was met with this response: "Ferruccio, you are just a farmer. You should focus on tractors and stay out of sports cars." Those words were the point of no return. Lamborghini resolved to build his own supercar that would surpass Ferrari. He hired the best engineers, including Giotto Bizzarini, the person who had developed engines for Ferrari. The team created that same legendary engine that became the heart of the first Lamborghini 350 GT. Even then, the car showed that Lamborghini was not joking around. It was faster and more comfortable than Ferrari. The first car was a success, and the company began to grow rapidly. Within only a few years came the legendary Misura, then the Countach, the Diablo, the Murcielago, and the Aventador. And now, for 60 years, Lamborghini has continued to be a symbol of status, aggression, and an engine's ferocious roar. The main Lamborghini factory covers 1,743,752 square feet. That is nearly the size of 23 soccer fields. This place is a genuine temple of speed and engineering artistry. All the critical steps in creating supercars are concentrated here. Massive pavilions equipped with ultra-modern technology merge with the craftsmanship of hand assembly, which remains an unchanging tradition of the brand. The factory includes a materials laboratory where carbon fiber is tested, paint booths where each automobile receives a perfect finish, and the exclusive ad personam division that allows clients to customize their Lamborghinis down to the finest detail. Every vehicle undergoes strict quality tests before leaving this temple of speed, bound for owners all over the world. In the year 2023, Lamborghini set a production record for the entire history of the company. 8,405 brand new cars rolled off the factory line. Every contour of the body is designed not only for aerodynamics, but also for maximum visual impact. The low profile, the aggressive front end, the sharp edges, and the massive air intakes all form the image of a wild predator ready to pounce. The signature guillotine doors on the Aventador or Revuelto models are an unforgettable sight. They lift upward. The moment you open them, you already look like a movie star. Buying a Lamborghini is not simply about money. It is about a way of life. Lamborghini owners want to stand out, be at the center of attention, and experience an adrenaline surge each time they press the gas pedal. It is no surprise that among these owners are soccer players, actors, business people, and even princes. Lamborghini has always been synonymous with exclusivity. Production is limited. Most models are released in small batches, and some appear in limited runs of 10 or 20 units. For example, the Lamborghini Centenario was produced in only 40 units, 20 coupes, and 20 roadsters. Lamborghini uses only premium materials, most of which come from the world's top suppliers. The main material is carbon fiber. Did you assume the body was made of metal? It is not. Carbon fiber is an ultra-strong yet lightweight material made up of extremely thin strands of carbon, each roughly 10 times thinner than a human hair. It is stronger than steel, but weighs several times less, making it ideal for supercars. Carbon fiber begins with polyacrylonitrile threads, which are a synthetic material similar to plastic. The fibers are heated in special furnaces with oxygen, which alters their chemical structure and makes them thermally stable. Then the fibers move into furnaces without oxygen, for instance in a nitrogen atmosphere. Under extreme temperature, they lose all inorganic components and are left as nearly pure carbon. These carbon threads are then treated to bond more effectively with polymer resins. The finished fibers are woven into fabric or laid out as ribbons. The carbon fabric is infused with resin and then shaped as needed. Lamborghini uses forged composites technology, where the fibers are arranged randomly, resulting in parts that are even lighter and stronger. The form goes into a high-temperature, high-pressure autoclave, where the composite hardens and gains extraordinary rigidity. Imagine strands thinner than a hair passing through furnaces at 3,632 degrees Fahrenheit. What comes out is a black thread that is 5 times stronger than steel, yet 7 times lighter. Instead of a conventional steel component weighing 33 pounds, Lamborghini gets a carbon substitute that weighs 6 pounds, while preserving the same strength. This material enables Lamborghini to craft bodies that are light, strong, and fast, reducing the vehicle's overall mass and boosting its aerodynamics and performance. Aluminum is sourced in Europe, especially from Italy and Germany. It is utilized for fabricating the chassis, the load-bearing body components, and various structural parts, since it is both light and strong. Suppliers deliver aluminum as sheets, profiles, or ingots. When it arrives as ingots, it is melted down and cast into blanks. Aluminum is melted in special furnaces at around 2,232 degrees Fahrenheit. The molten metal is poured into molds under high pressure. The casting solidifies in a matter of seconds and is then removed. The cast pieces are ground, excess material is trimmed off, and they undergo heat treatment to enhance their strength. Using aluminum makes the frame about 40% lighter than a steel alternative. Lamborghini's press machines can produce up to about 11,000 short tons of forming pressure. A single aluminum Aventador frame weighs a mere 504 pounds, which is essential for high speeds and maneuverability. Natural Italian leather arrives from renowned tanneries in Tuscany and Piedmont. Alcantara is sourced from a factory in Umbria for the upholstery. Carbon inserts are produced directly at Lamborghini. It may require 7 or even 8 cowhides to upholster the interior of one Lamborghini. Buyers can choose any color of leather via the Ad Personam personalization program. Lamborghini uses premium Napa leather and aniline leather, which both have a natural texture and softness. All leather sections are handcrafted to maintain exclusivity. The leather is manually cut for each part to avoid defects or unevenness. Every seam is also stitched by hand, ensuring precise quality control. Special leather threads are used for this purpose. Each piece is dyed and treated to achieve the requested appearance and texture, consistent with the client's wishes. Once every piece is ready, it is assembled and installed in the automobile. Alcantara is a high-end synthetic material that resembles suede in both look and feel. It is widely applied in the automotive sector. Alcantara is soft, matte, and holds up better to wear than genuine leather. It is also twice as light as leather, which is critical for supercars. It does not fade, retaining its color even under direct sunlight, and it is made of 68% recycled materials. The assembly process begins with preparing the vehicle body and chassis. This involves installing a foundation constructed from lightweight metals or carbon fiber, depending on the specific model. At this stage, every mainframe element is brought together, including the suspension, the exhaust system, and other key components. This step is of the utmost importance, as it lays the groundwork for everything that comes afterward. The body is assembled by hand, using specialized tools and fixtures to ensure maximum precision and minimal gaps. Once the body and chassis are complete, the next step is the installation of the engine and the transmission. The engine is the heart of a Lamborghini, and putting it in place is an exceptionally intricate process. All Lamborghini engines are built and tested separately prior to being mounted in the car. Installing the engine also requires connecting it to the cooling system, the exhaust, and the vehicle's electronics. After this, the gearbox and the transmission system are fitted, allowing the engine's power to be transferred to the wheels. During this phase, all of the vehicle's critical systems are also fine-tuned, including the suspension and braking systems. The following stage involves installing the car's interior parts. This includes the seats, the instrument panels, the door trim, and the steering wheel. All these elements are made by hand using superior quality leather or Alcantara, in the case of sportier versions, along with other exclusive materials. Every piece is finished with meticulous attention to detail, creating a truly unique cabin. For instance, Lamborghini seats are crafted by hand to accommodate every curve of both driver and passenger, providing outstanding comfort. The steering wheel is also handmade and can feature a personalized design, according to the client's preferences. Once the principal interior components are set, the car moves on to the phase dedicated to connecting the electronic systems. Lamborghini cars are noted for their cutting-edge technology, so they come equipped with intricate infotainment setups, navigation, touchscreens, and safety systems. All wires and electronic parts must be hooked up with extreme accuracy to avoid errors or malfunctions. This process can take several hours and calls for highly qualified technicians who precisely follow each component's wiring diagrams. Having finished the physical assembly of the automobile, Lamborghini proceeds with the testing stage. Each vehicle goes through a detailed evaluation on special test stands, where every function and system is checked, ranging from the engine and transmission to the brakes and suspension. This helps detect any faults or issues before the car reaches the end buyer. One of the most vital segments of testing is assessing the car's performance dynamics on the track. Here, the automobile's characteristics at high speeds are evaluated, along with its maneuverability, braking force, and stability when cornering and accelerating. Once all tests have been completed, the car returns to the assembly hall for a final inspection. If all systems operate correctly, the vehicle undergoes one last quality assessment. After this, it receives finishing touches, such as body polishing and a thorough check of every surface for paint defects. At Lamborghini, each car has its own special color, chosen during the production phase. After this, it receives finishing touches, such as body polishing and a thorough check of every surface for paint defects. At Lamborghini, each car has its own special color, chosen during the production phase. Every year, over 2,200 million pounds of edible insects are produced worldwide. They are dried, ground, and added to cookies, snack bars, and even cheese filled with live larvae. The biggest farms are now being built across tens of thousands of acres, not just in Asia, but in Canada, Spain, and the United States too. Crickets, beetles, locusts, they are crashing into the future of food. Why? They are cheaper than meat, healthier than fish, and 100 times more eco-friendly than beef. In this video, we will show you what these farms look like, how insects are raised, and how they end up on our plates. Right now, several companies are competing for the title of the world's largest edible insect farm. Let me tell you a bit about each. In January of the year 2025, the company Tebrio began building a farm called O Farm in Salamanca. When finished in the year 2028, it is expected to cover over 22,000 acres and produce more than 220 million pounds of insect-based products annually. In September of the year 2023, the company Cricket One launched Asia's largest cricket processing plant in Binh Phuoc province. The initial capacity is about 2,205,000 pounds per year, with plans to scale up to over 22 million pounds in 5 years. Hold on, let me take a sip of water while the insectophobia exits our chat. In London, Ontario, Aspire Food Group built a 150,000 square foot facility, considered the world's largest cricket processing plant. The title of largest edible insect farm changes constantly due to the rapid growth of this sector and new projects launching all the time. You might ask, why? Or maybe you are speechless already. But here's the thing. In more than 100 countries, insects have been part of the diet for centuries. For people in Thailand, Mexico, and parts of Africa, it is just normal food. In Thailand and Laos, the beetle Lithocarus indicus is used as a spice. Its internal extract tastes like green tea and mint. People squeeze it like a lemon. Just imagine. A little beetle on your salad, and you are good to go. In Sardinia, there is a cheese with live larvae. It is officially banned, but highly prized by locals. It is made from sheep's milk, and the larvae actively move and digest the cheese, giving it a soft texture and sharp flavor. People eat it with the larvae, alive. If the larvae are dead, the cheese is considered spoiled. In Cambodia, fried tarantulas are a popular delicacy. They are said to taste like a cross between crab and chicken. People break off the legs, remove the venomous fangs, and enjoy a crunchy lunch. In Japan, tiny beetles are used in fermenting traditional foods as natural preservatives. For example, in making soy sauce or fermented paste, a bug-based microflora is used to give the right smell and texture. In the European Union, yellow mealworm larvae flour is now legally approved for food. It is high in protein and nearly tasteless. So now there are breads, cookies, and pasta made from insect flour. In many countries, insects are not served as, hey, here is a fried grasshopper with legs, but are ground into flour and added to snacks or protein bars, looking just like regular food. Insects are rich in protein, iron, omega-3, and vitamins. Many are as nutritious as meat. For example, crickets contain 70% protein by weight. Insects reproduce quickly. For farmers, this is a win. One full cycle takes just weeks, not years. Unlike cows or pigs, insects need far less water, feed, and space. They also emit fewer greenhouse gases. Perfect for the planet. Officially and legally, the most commonly farmed insects are crickets, mealworms, and locusts. Farms usually specialize in one insect species for efficiency. This helps streamline operations and reduce management costs. Insects have different needs: temperature, humidity, and feed. So it is easier to focus on just one species per farm. However, some farms raise multiple insects, like combining crickets and mealworms, or create zones for each, if it makes economic sense. A cricket farm is a structured system where insects are raised specifically to produce protein used in food, feed, or even the cosmetics industry. Such a farm can be a small business or a large commercial facility, producing thousands of tons of protein each year. The first thing a cricket farm needs is a properly equipped space. This could be large containers or racks with boxes or trays for breeding and raising crickets. Temperature and humidity are critical. It should not exceed 90 degrees Fahrenheit, and humidity should be between 50 and 70%. Crickets also need a light cycle, so artificial lighting is sometimes used to maintain optimal conditions. Choosing the starter insects is key. Special breeding cages are set up where adult crickets reproduce, and the eggs are transferred to other containers to develop. Crickets go through several life stages: egg, larva, nymph, and adult. This process takes 6 to 8 weeks. During their lives, crickets consume a lot of feed. Typically, this includes wheat bran, vegetables, fruits, and special mixed feeds, providing all necessary nutrients. They eat actively, so farmers must regularly replace food and check its quality to prevent disease outbreaks. Once crickets mature, they are harvested. Farms use special equipment to separate adult crickets from the substrate and sort them for further processing. Usually, crickets are either dried or frozen before being turned into powder. That powder is then used to make feed, energy bars, or even dietary supplements for humans. A critical part of the farming cycle is cleaning the breeding containers to prevent pests and disease. After harvesting, farmers clean all trays, change substrates, and sometimes add new insects to replenish the population. Proper waste management is also important, since leftover food and insect waste must be disposed of safely. After crickets are processed, they are either dried or turned into powder, depending on the product being made. If it is animal feed, the insects are simply dried and crushed. For food supplements, the process is more complex, involving special machines to retain all the nutrients. Technology on these farms is constantly improving, because this is a business built for an eco-friendly and sustainable future. A farm like this can be fully self-sufficient, using organic waste for feed, making it both economical and green. Mealworms are another popular insect raised for protein. They have great potential in the food industry, for both animal and human consumption. Mealworms belong to the beetle family, and are often farmed because they are easy to raise and high in protein. Mealworm farms usually have several rooms or trays where ideal conditions are created for reproduction and growth. The perfect temperature is between 170 and 186 degrees Fahrenheit, and humidity must stay low to avoid mold or disease. They need dim lighting, so these farms often operate in low-light environments. The process starts with introducing the starter material, mealworm eggs, which are placed in containers with substrate for incubation. Eggs develop into larvae over several weeks. These larvae are protein-rich and used for animal feed or ground into food supplements. After 2 or 3 months, larvae transform into pupae, then into adult beetles. For healthy development, mealworms need moist, fiber-rich substrates like wheat bran, cornmeal, or even vegetables and fruits. They feed actively on the substrate, which also helps recycle organic waste. Farmers must regularly change the feed, check moisture levels, and inspect for parasites. Yes, you read that right. Mealworms can have their own parasites. I will never look at protein the same way again. Once the larvae are big enough, they are collected, by hand or with machines. After harvest, they are either frozen or dried. The dried mealworms become the base for pet food or protein-rich human food products. After harvesting, containers must be cleaned of leftover feed, insect waste, and dead bugs. Clean environments are crucial. Substrates should be regularly replaced to prevent harmful microbes. Locusts are another insect raised for protein, but they are much more demanding. Locusts are your high-maintenance girlfriend in the insect world. They need attention. Farms for locusts often include large greenhouses or special buildings that mimic natural habitats. The temperature must be around 85 degrees Fahrenheit, and humidity should not drop below 50%. They also need plenty of space to reproduce and grow. Locusts reproduce by laying eggs, which are incubated in warm, moist conditions. Once hatched, the nymphs look like adult locusts, but without wings. They need time to grow into fully mature insects. Locusts are herbivores, so farms feed them grasses, leafy greens, and vegetables like cabbage or carrots. Proper nutrition is key to a healthy population and high protein content in the final product. Now the girlfriend comparison ends, because once locusts reach maturity, they are collected, separated from the substrate, and processed. Usually, they are frozen or dried. After drying, they can be turned into powder for animal feed, food additives, or even cosmetics. Like with other insects, locust farms must be cleaned regularly to prevent disease and maintain healthy conditions. The production models for mealworms and locusts are similar, even though their needs and diets differ. This allows farms to maintain consistency and ensure high-quality products. So, what will you choose? Potatoes, or some surprisingly healthy insects? Imagine this. Every year, more than 50 million drums are made around the world. But have you ever wondered how a piece of wood becomes a powerful instrument that sets the rhythm for music? From ancient shamanic rituals to modern rock arenas, drums have always been the heart of sound. To create the perfect drum, wood is dried for years, metal parts are crafted with jewelry-like precision, and membranes undergo special treatments. Today, we're going inside this process, step by step, from the lumber mill right onto the stage. The drum is one of the oldest musical instruments in the world. Its history stretches back at least 7,000 years, perhaps even more. The earliest drums were simple, animal skins stretched over wooden or clay bases. Over time, they evolved into the complex structures made from various materials that we see today. The oldest drums found by archaeologists date back to 5,000 years before Christ. They have been discovered in Africa, Mesopotamia, China, and Egypt. These early drums featured clay or wooden bodies with animal skin membranes stretched with ropes or glued on with resin. In shamanic rituals and religious ceremonies, drums were used to communicate with spirits. In ancient China and Egypt, drums coordinated armies on battlefields. In some African tribes, drums were even used to send messages over long distances. In the Middle Ages, drums became popular in Europe thanks to the Arabs, who brought them through Spain during the Muslim conquests. During this period, drums became integral to military music and later orchestras. A drum isn't just a chunk of wood or metal. Every part matters. The shell, the membrane, the hoops, bolts, and even the drumsticks. All these elements are crafted from carefully selected materials, and each affects how the instrument sounds. Wood used for drum shells must be properly dried, processed, assembled, and finished with lacquer. Metal parts are cast, polished, and protected against corrosion. The process is more complex than it first appears. Let's dive deeper into these details. Wooden drums have a special warmth to their sound. But as we said before, creating such a shell first requires carefully selecting, preparing, and drying the wood. The most popular choice for drum shells is maple. It produces a warm, balanced tone with excellent lows, mids, and highs, making it a staple in most studio and live drums. Birch provides a bright, aggressive sound, boosting the highs and lows, perfect for rock, metal, and live performances. Mahogany offers a deep, bass-rich sound with mellow highs, famously used in vintage drums from the 1950s and 1960s. Bobinga, a dense African hardwood, delivers a darker, powerful tone with great attack. More expensive, it's reserved for premium models. Oak, harder than maple, provides an exceptionally loud, penetrating sound ideal for live settings. Simply cutting down a tree and slicing it into boards is just the beginning. The tree must be harvested in a specific season, usually winter, when it contains the least moisture. Logs without cracks or knots are chosen. Freshly cut wood can have up to 60% moisture. First, the wood air dries outdoors for several months or even years. Then it undergoes kiln drying, reducing moisture content to between 8 and 12%. Next, boards are sliced into thin layers called plies, glued together under high pressure. The thickness of these wooden plies typically ranges from 0.024 inches to 0.118 inches. To produce uniform, thin layers without excess waste, several methods are used. Rotary cutting involves mounting logs onto special machines that spin them while blades peel thin, continuous wood strips, typically for budget drums. Bandsawing uses a flexible, continuous saw blade, moving in a loop to cut logs into thin plies. This method provides more precise cuts than rotary peeling, and preserves the wood grain better, although it creates more waste. For high-end drums showcasing exotic wood grains, manufacturers employ veneer slicing. Logs or boards are fixed, then moved against a sharp blade to shave off thin sheets. Laser cutting is the least common method. Premium drums sometimes feature solid wood shells, providing unique tonal qualities. But today, we're not focusing on those. Let us know in the comments if you'd like a separate video dedicated to that topic. First, the plies are coated with special glue, then stacked, forming a multi-layered structure. The number of layers typically varies from 4 to 20, depending on the desired shell thickness. Next, this stack is placed into specialized molds, bending the wood into a perfectly round cylinder. Even pressure is crucial to prevent defects and air bubbles in the glue. Afterward, the shells dry for several hours or even days. Once the glue hardens, shells are removed, edges trimmed, sanded, and drilled for hardware. This method is economical and allows manufacturers to experiment with combinations of wood types to influence sound characteristics. Polishing and applying finishing coatings is primarily manual work, especially for high-quality or custom drums. Shell surfaces are carefully sanded, removing all irregularities. Sanding happens either by hand or machine, progressing from coarse to extremely fine abrasives, usually from 120 to 400 grit. For glossy lacquer finishes, manufacturers may first apply primer to prevent excessive absorption by wood pores. Oil or wax finishes are rubbed in manually using soft cloths or brushes, penetrating deeply into the wood pores, protecting from moisture and enhancing the natural color. Lacquer is sprayed in several thin layers, drying completely between each coat. This process is performed by skilled artisans manually or by automated equipment in large factories. After drying, shells receive a final polishing to achieve the desired gloss, ranging from matte to mirror-like shine. In large companies like Pearl or Yamaha, producing hundreds of drums, lacquer is applied automatically. Still, final finishing always occurs by hand, since even the best machines cannot match human precision. Boutique manufacturers such as Cravioto, Brady, or Noble & Cooley finish every shell entirely by hand, making each drum unique and even more expensive. Even wooden drum shells have numerous metal parts: hoops, tension rods, and grommets. Hoops are typically chrome-plated steel, brass, aluminum, or even wood. Tension rods are commonly stainless steel or brass. Grommets are small metal inserts reinforcing the drilled holes in the shell. How are metal parts produced? Metal is melted at high temperatures, then cast or machined into required shapes. These parts are sanded and polished, removing roughness, then coated with protective layers like chrome or nickel to prevent rust. Historically, drums featured animal skins: cow, goat, or buffalo. Nowadays, synthetic plastics are more common due to their stability, durability, and weather resistance. Natural animal skin, being organic, expands and contracts with humidity and temperature changes. Moisture makes skins softer and sounds duller, whereas dry conditions cause them to shrink and crack. Synthetic materials maintain consistent tension regardless of weather. Once tuned, synthetic drumheads remain stable until manually adjusted. Drumhead materials, whether skins or plastic, are cut into circular pieces, treated chemically for flexibility, then pressed and stretched onto metal hoops. Preparing animal skins is truly spectacular. Inside large workshops, air smells of smoke, salt, and something sharp. Huge wooden vats line the walls, holding pieces of skin that visibly change color. This isn't mere soaking. It's true alchemy transforming tough, uneven hides into perfect drumheads. Initially, skins soak in large vats containing lime solutions, softening them and removing hair. After several hours or days, skins become lighter but still coarse. Next, they're treated with tanning substances, penetrating their structure on a molecular level. Vats emit steam. The aromas of wood, metal, and rawhide blend in the air. To avoid excessive stiffness, skins are stretched onto large wooden frames. Craftsmen stretch the skins manually, feeling thickness with their fingers. Sometimes steam is used, filling the workshop with thick vapor as skins are warmed before final treatment. Lastly, skins are rubbed with special mixtures: oils, waxes, sometimes herbal extracts. This keeps them flexible yet strong. In some regions, they're even smoked, imparting a light, smoky scent and improved water resistance. Even the best drum won't sound great without proper drumsticks. These are also crafted from carefully selected wood. Wood, typically hickory, maple, or oak, is sawn into blanks and air-dried naturally. But this takes time, so kilns usually speed the process, carefully controlling temperature and humidity, aiming for moisture content of 6 to 8%. Correct moisture levels are critical. Too moist, sticks warp. Too dry, they become brittle. Dried blanks are shaped on high-speed lathes. Each stick must have identical diameters. Otherwise, sticks within pairs produce different sounds. Simply turning a round stick isn't enough. Tip shape, taper in the middle, and weight distribution define how sticks sound when striking drums. High-speed lathes achieve precision within thousandths of an inch to ensure consistent quality. What do a sandwich, potato wedges, and pasta have in common? That's right, cheese. It takes these simple dishes and turns them into pure bliss. There are plenty of cheeses in the world, but cheddar holds a special place in my heart. Today we're diving into my love story with this cheese, my go-to for the easiest, most delicious meals I know. Let's get started. At the cheese factory where cheddar is made, pasteurization is like a technological dance. By the way, are you into techno? The process kicks off with an automated system moving milk through a network of sterile pipes to a pasteurization unit. Here, heat exchangers warm the milk to an exact temperature, typically between 161 and 167 degrees Fahrenheit. It's not just heating, it's a precision process that destroys harmful microorganisms while keeping the milk's nutrients intact. The secret lies in the control system. High-precision sensors continuously monitor the milk's temperature. Once the milk has been heated for the required time, it's cooled down almost instantly to a safe 39 degrees Fahrenheit. Here's where it gets innovative. The heat released during cooling is reused to warm the next batch of milk. This energy regeneration is both cost-effective and eco-friendly, reducing the production's overall energy consumption. In the warm halls of the cheese factory, where the milk has already been pasteurized, the next step begins, adding the starter culture and rennet. The pasteurized milk is poured into large stainless steel vats, where it's heated to around 86 to 89 degrees Fahrenheit, the perfect temperature for the starter culture to do its magic. A computer system controls every detail, from the milk volume to the exact temperature in each vat. The starter culture goes in first. These are carefully selected lactic acid bacteria that give cheddar its signature flavor and texture. Delivered as either a powder or liquid, the culture is measured precisely by robotic dispensers. Once added, large mechanical paddles gently stir the milk, ensuring the bacteria are evenly distributed. Next comes the addition of rennet, a microbiological enzyme called renin. It's eco-friendly and even suitable for vegetarians. Adding rennet is where the magic happens. It transforms the milk into a curd in less than an hour, laying the foundation for cheddar. While the rennet works its magic, the system keeps an eye on every change in the milk. Sensors measure acidity and density, while algorithms determine the exact moment to end this phase. Modern technology ensures the process is quick, efficient, and requires minimal human intervention. Once the curd is fully formed, the milk is no longer a liquid. It has become a smooth, tender cheese mass, ready for the next step in becoming the famous cheddar. Cheddar is the reason I took my first steps in cooking. Actually, I've taken a lot of steps since then, but I still feel like I'm standing in the same spot. But let's not talk about that. Let's talk about 10-year-old me trying to cook for the first time. Picture this. Me, a heated pan. My mom watching from the corner of the kitchen, ready to call 911 if needed. And there they were. 2 slices of bread slathered with butter and a generous slice of cheddar. Sure, the bread got a little burnt, but it still tasted incredible. By the way, what was the first thing you ever cooked? Forming the curd is when cheddar starts to take physical shape. Every parameter, temperature, acidity level, enzyme timing, is carefully monitored. Sensors continuously measure the milk's density to determine when the curd has reached the ideal consistency, which takes about 30 to 40 minutes. Look at this giant vat. The milk seems to have frozen in time, turning into a soft, gel-like curd. Once the sensors confirm the curd's structure, special knives come into play. These are automated paddles fitted with blades that gently cut the curd into small cubes. They move slowly and evenly to maintain uniformity, which is essential for separating the whey later. At the same time, the vat is gradually heated to around 100 to 104 degrees Fahrenheit. This secondary heating helps expel whey and solidify the cheese granules. As the whey separates during heating, it's drained through special valves at the bottom of the vat. This process is also automated, ensuring just the right amount of whey is left to maintain the cheese mass's proper consistency. What remains in the vat is dense yet tender curd, ready for the cheddaring process. You've been waiting for this part, haven't you? The curd, now formed into large chunks, is transferred to special tables or conveyor belts made of stainless steel with built-in heating systems to maintain the optimal cheddaring temperature of around 95 to 100 degrees Fahrenheit. The curd is stacked into layers, distributed evenly by robotic manipulators or conveyor systems. These layers rest for a specific time, allowing them to bond and compress. Under its own weight and the steady temperature, the curd releases residual whey. After a certain period, the layers are flipped over. A key feature of the cheddaring process is the gradual acidification of the curd. This happens thanks to the lactic acid bacteria added earlier with the starter culture. Their activity alters the cheese's chemical composition, giving it a mild, slightly tangy flavor. By the time cheddaring is complete, the curd becomes dense, elastic, and ready for the next step, cutting and salting. Automated cutting systems divide the curd into equal pieces, ensuring consistent weight and size for every portion. At this point, my friend, we're one step closer to achieving cheddar's authentic flavor and texture. Now the curd, firm and springy, moves along specialized conveyors. Come closer and take a look. This is where the curd is cut into blocks or cubes, depending on the intended product. Next, it's time for salting. In the US, two main salting methods are used: brine baths and dry salting. The choice depends on the recipe for each batch of cheddar. In brine baths, large tanks are filled with a salt solution, where the cheese is submerged for several hours to allow the salt to penetrate its structure. For dry salting, the cheese blocks travel along a conveyor, passing through machines that evenly sprinkle salt over them. Salt serves a dual purpose. It enhances flavor and acts as a natural preservative, protecting the cheese from unwanted microorganisms. During this stage, the cheese continues to release residual whey, which automated systems collect and process for further use or recycling. And now, it's time for aging. This, by the way, is something I have zero patience for when it comes to cheddar. The cheese blocks are sent to special aging rooms, also known as maturation chambers. These chambers are equipped with modern climate control systems that automatically maintain optimal conditions for cheddar to age. Temperature, humidity, and air circulation are regulated with precision, down to the 10th of a degree or percentage, because even the slightest deviation can impact the cheese's quality. Cheddar is typically aged anywhere from a few months to several years. Young cheddar has a mild, creamy taste, while aged cheddar develops a rich, tangy flavor with a crystalline texture. The aging duration is determined during the batch planning stage, and all parameters are recorded in a centralized computer system. Robotic manipulators carefully stack the cheese blocks on racks in the aging chambers. These robots are programmed to minimize contact with the product, ensuring a high level of hygiene. The rack systems are also automated, capable of rotating or moving the blocks for even aging. Throughout the aging process, the cheese is closely monitored. Automatic sensors in the chambers continuously check the microclimate and even analyze gases released by the cheese to track chemical changes in its structure. In some cases, cheddar is coated with a layer of wax or a special film to protect it from drying out and environmental exposure. For aged varieties, dry aging is sometimes used, leaving the cheese uncovered to form a natural rind. When this method is chosen, automated systems periodically move and flip the blocks, cleaning them of any accumulated dust or mold.